Right now, as you sit here watching this video, I want you to consider something absolutely extraordinary. You are not sitting still. You think you are, but you are not. The Earth beneath you is spinning at roughly 1,670 kilometers per hour. The Earth itself is hurtling around the Sun at about 107,000 kilometers per hour. The Sun is dragging our entire solar system around the center of the Milky Way galaxy at approximately 828,000 kilometers per hour. And on top of all of that, our galaxy is rushing through the cosmos at around 2.1 million kilometers per hour relative to the cosmic microwave background radiation. You are moving right now at a staggering combined velocity through space, and you cannot feel a single bit of it. But here is the part that will truly break your mind. Even with all of that motion combined, all of that incredible speed stacked on top of speed, stacked on top of speed, you are not even scratching the surface of the fastest thing in the universe: light. Light travels at 299,792,458 meters per second, every single second, without fail, without slowing down, without speeding up, without needing fuel or force or anything at all. In 1 second, a beam of light can circle the entire planet Earth 7.5 times. In 8 minutes and 20 seconds, light crosses the 93 million miles between the Sun and our eyes. In 1 year, light travels about 9.46 trillion kilometers, a distance so enormous that we had to invent a special unit just to describe it: the light year. And this speed, this specific number, is not just some arbitrary cosmic record. It is the absolute, fundamental, unbreakable speed limit of the entire universe. Nothing that carries mass, nothing that carries energy, nothing that carries information has ever been observed to exceed it. Not in any experiment, not in any observation, not anywhere in the cosmos, not once in the entire history of science. But wait, if that is true, then how do we explain the fact that right now, at this very moment, there are galaxies moving away from us at 3 times the speed of light? How do we explain the fact that scientists in 2024 confirmed that darkness, actual darkness, can travel faster than light? How do we explain the fact that if you take a simple laser pointer and sweep it across the surface of the moon, the dot moves faster than light? How do we explain the fact that in 2011, the most advanced physics laboratory on the planet announced that they had detected particles traveling faster than light, and the entire scientific world went into a state of absolute panic? These are not hypothetical questions. These are real observations, real experiments, and every single one of them seems to suggest that maybe, just maybe, light's speed limit is not as absolute as we have been told. So which is it? Is the speed of light truly the ultimate unbreakable barrier? Or are there cracks in the wall? Are there loopholes? Are there ways around it that the universe has been hiding from us all along? That is exactly what we are going to explore in this video. And I do not mean a surface-level overview. I mean we are going to go all the way from the very first human being who tried to measure the speed of light over 400 years ago, through the mind-bending genius of Einstein, through the bizarre world of quantum mechanics, through the vast expansion of the universe itself, all the way to the latest cutting-edge research. We will examine every single thing that appears to travel faster than light, and we will determine exactly which ones are genuine violations and which ones are clever illusions. We will look at real experiments, real numbers, real physics, no speculation, no science fiction, just the raw, stunning, almost unbelievable truth about the fastest speed in the universe, and whether anything can beat it. And I promise you, by the end of this journey, the answer will surprise you in ways you do not expect. If you are someone who loves having your mind expanded by deep science content, then do me a favor right now. Hit that subscribe button, turn on notifications, and drop a comment telling me what you think the answer is. Can anything truly travel faster than light? Let me see your answer before we dive in, because by the end of this video, your answer might be very different. Let us begin. To understand why the speed of light is so special, we first need to understand something that might seem surprising. For most of human history, people did not even believe light had a speed at all. Think about that. For thousands of years, the greatest minds on Earth looked at light and thought it appeared everywhere simultaneously, instantaneously, that when you lit a candle, the The light filled the room not quickly, but immediately, with no delay whatsoever. This was not a fringe belief. This was the dominant view of some of the most brilliant thinkers who ever lived. The ancient Greek philosopher Aristotle, one of the most influential minds in Western history, argued explicitly that light does not travel. He believed light was not a thing that moves from one place to another. Instead, he thought it was a state, a condition of the medium between the object and the eye. When the sun rose, the air did not gradually fill with light streaming outward. Rather, the medium itself changed state all at once, and light simply was. No motion, no speed, no travel time, instantaneous presence. But not everyone agreed. Another Greek philosopher, Empedocles, who lived about a century before Aristotle, around 490 to 430 BC, proposed something radically different. He suggested that light actually does travel from its source to the observer, and that this travel takes time. It might be an incredibly small amount of time, too small for humans to notice, but it is not zero. Light, Empedocles argued, is something that moves, and anything that moves must take some amount of time to get from one place to another. This was an extraordinary insight for its time, but Aristotle's enormous intellectual authority overshadowed it. For the next 2,000 years, the idea that light was instantaneous held sway across Europe and much of the world. Then came the Islamic Golden Age, and with it, one of the most important scientists in human history, a man whose contributions to optics are so profound that he is sometimes called the father of modern optics. His name was Ibn al-Haytham, known in the Western world as Alhazen, and he lived from around 965 to 1040 AD. In his monumental work Kitab al-Manazir, the Book of Optics, written around 1011, Ibn al-Haytham made arguments that were centuries ahead of their time. He proposed that light is a physical entity that travels from luminous objects to the eye, not the other way around as some Greek thinkers had suggested. And critically, he argued that because light is physical, because it is a real thing that moves through real space, it must have a finite speed. It cannot be instantaneous. Ibn al-Haytham could not measure this speed. He lacked the tools, but his reasoning was sound. Light is a thing. Things move through space. Moving through space takes time. Therefore, light takes time to travel. Simple, elegant, and correct. But measuring that speed, that remained an impossibly difficult challenge. Light is so fast that no experiment of that era could detect its travel time over any distance accessible to humans. And so the debate lingered, unresolved, through the Renaissance and into the scientific revolution. The first person in recorded history to actually attempt a measurement was the great Italian physicist and astronomer, Galileo Galilei. In the early 1600s, Galileo devised an experiment that was brilliant in its simplicity. He and an assistant each stood on different hilltops, approximately 1 mile apart. Each held a covered lantern. The idea was straightforward. Galileo would uncover his lantern, sending light toward his assistant. The moment the assistant saw the light, he would uncover his own lantern, sending light back to Galileo. Galileo would then try to measure the total time between uncovering his lantern and seeing the return flash. If light had a finite speed, there should be a detectable delay. Galileo ran the experiment, and the result was nothing. He could detect no delay whatsoever. The light appeared to travel between the hilltops and back instantaneously, at least as far as his ability to measure was concerned. But Galileo, being the extraordinary scientist he was, did not conclude that light was infinitely fast. Instead, he drew a more careful conclusion. He wrote that if light was not instantaneous, it was at the very least extraordinarily rapid. He recognized that the failure was in his measurement capability, not necessarily in the theory. The hilltops were too close. Human reaction time was too slow. The speed of light was simply too fast for his method to capture. Galileo's experiment failed to measure the speed of light, but it succeeded in something perhaps more important. It established the principle that the speed of light is a question that should be answered by experiment, not by philosophy. It moved the question from the realm of abstract debate into the realm of empirical science, and that shift would eventually lead to one of the most stunning discoveries in the history of astronomy. The breakthrough came in 1676, and it came from an unexpected source. A Danish astronomer named Ole Rømer was working at the Royal Observatory in Paris, not studying light, but studying the moons of Jupiter. Specifically, He was meticulously tracking the orbit of Io, the innermost of Jupiter's 4 large moons discovered by Galileo. Io orbits Jupiter in approximately 42.5 hours, a beautifully predictable celestial clock. Rømer was using Io's regular eclipses, the moments when it disappeared behind Jupiter, to create astronomical tables for navigation. But as he compiled months and months of careful observations, he noticed something strange. The timing of Io's eclipses was not perfectly consistent. Sometimes, the eclipses happened slightly earlier than predicted. Sometimes they happened slightly later. The variations were small but unmistakable, and they followed a clear pattern. When Rømer plotted the discrepancies against Earth's position in its orbit around the Sun, the pattern became obvious. When Earth was moving toward Jupiter in its orbit, Io's eclipses came slightly early. When Earth was moving away from Jupiter, the eclipses came slightly late. The maximum discrepancy was about 22 minutes over the course of half a year. And then came Rømer's flash of genius. The variations had nothing to do with Io's orbit. Io was a perfect clock. The variations were caused by the changing distance between Earth and Jupiter. When Earth was closer to Jupiter, light from the eclipse had less distance to travel, so it arrived sooner. When Earth was farther from Jupiter, the light had more distance to cover, so it arrived later. The 22-minute variation corresponded to the extra time light needed to cross the diameter of Earth's orbit around the Sun. From this, Rømer calculated the speed of light at approximately 220,000 kilometers per second. This was not perfectly accurate. The modern value is about 299,792 kilometers per second, but it was extraordinary for the 1670s. More importantly, it was the first definitive proof that light has a finite speed. It was not instantaneous. It traveled, and it traveled fast, but not infinitely fast. A 2,000-year debate was finally settled, not by philosophy, but by the moons of Jupiter. About 50 years later, in 1729, an English astronomer named James Bradley provided stunning independent confirmation. Bradley was studying stars, not moons, and he noticed that the apparent positions of stars shifted slightly over the course of a year. This phenomenon, called stellar aberration, occurs because Earth is moving around the Sun while starlight travels toward us. It is exactly analogous to the way rain appears to fall at an angle when you run through it, even if it is actually falling straight down. The angle of the aberration depends on the ratio of Earth's orbital velocity to the speed of light. By measuring this angle, Bradley calculated the speed of light at approximately 301,000 kilometers per second. This was remarkably accurate, within less than 1% of the modern value, and it confirmed Rømer's finding completely. Light travels. It has a speed, and that speed is approximately 300,000 kilometers per second. Over the next century and a half, physicists refined this measurement with increasingly clever Earth-based experiments. In 1849, the French physicist Armand Fizeau performed the first successful terrestrial measurement of the speed of light. His apparatus was ingenious. He directed a beam of light through the gaps of a rapidly spinning toothed wheel toward a mirror positioned about 8 kilometers away. The light passed through a gap in the wheel, traveled to the distant mirror, reflected back, and returned to the wheel. If the wheel was spinning at just the right rate, the returning light would be blocked by the next tooth. By carefully adjusting the spin rate and knowing the distance, Fizeau calculated the speed of light at approximately 315,000 kilometers per second. Not perfect, but a remarkable achievement using nothing more than a spinning wheel and a mirror. 13 years later, in 1862, another French physicist named Léon Foucault improved on Fizeau's method by using a rotating mirror instead of a toothed wheel. This gave him a measurement of approximately 298,000 kilometers per second, extraordinarily close to the modern value. Foucault also made another critical discovery during his experiments. He showed that light travels slower in water than in air. This was a crucial piece of evidence supporting the wave theory of light, because the competing particle theory predicted the opposite, that light should travel faster in water. This single result helped settle one of the biggest debates in physics at the time. Then came Albert Michelson, an American physicist who became utterly obsessed with measuring the speed of light with the highest possible precision. Michelson developed an instrument called an interferometer, which could detect incredibly small differences in the behavior of light. Starting in 1879 and continuing for decades, Michelson refined his measurements to astonishing accuracy. In 1926, he conducted a definitive measurement between Mount Wilson and Mount San Antonio in California, using an improved version of Foucault's rotating mirror method across a carefully surveyed baseline of about 35 kilometers. His result was 299,796 kilometers per second, off by only 4 kilometers per second from the modern accepted value. For this and related work, Michelson became the first American to win the Nobel Prize in Physics in 1907. By the late 20th century, measurements of the speed of light had become so extraordinarily precise that a remarkable inversion occurred. The uncertainty was no longer in the speed of light itself, but in the definition of the meter. The meter, originally defined as 1/10,000,000th of the distance from the North Pole to the equator, had been refined multiple times over the centuries, but it was still ultimately tied to physical artifacts and measurements that had their own uncertainties. So in 1983, the General Conference on Weights and Measures made a historic decision. They defined the meter in terms of the speed of light. 1 meter is officially the distance that light travels in 1/299,792,458 of a second. This means that c equals 299,792,458 meters per second is now exact. By definition, the speed of light went from unmeasurable to estimated to precisely measured to finally becoming the very ruler by which we measure distance itself. That is how fundamental this number is. It does not just describe how fast light goes, it defines what a meter is. Now, I need to take you through one of the most beautiful and consequential discoveries in the history of science, because it reveals something profound about what the speed of light actually is. In the middle of the 19th century, electricity and magnetism were understood as two related but seemingly separate forces of nature. Michael Faraday had shown through brilliant experiments in 1831 that a changing magnetic field creates an electric current. Hans Christian Ørsted had shown in 1820 that an electric current creates a magnetic field. Electricity could produce magnetism. Magnetism could produce electricity. But the deep connection between them, the fundamental unity, had not been mathematically captured until a Scottish physicist named James Clerk Maxwell came along. Maxwell was one of the most remarkable minds in the history of physics, a man whose contributions Einstein himself regarded with enormous reverence. Einstein kept a photograph of Maxwell on the wall of his study. When asked whose work had most influenced his own, Einstein named Maxwell without hesitation, and for good reason. In 1865, Maxwell published a paper titled A Dynamical Theory of the Electromagnetic Field that would change physics forever. In this paper, Maxwell presented a set of equations, 4 elegant mathematical expressions that unified electricity and magnetism into a single framework called electromagnetism. These equations, now known as Maxwell's equations, described how electric and magnetic fields are created by charges and currents, and how they interact with each other. But the equations contained a stunning surprise. When Maxwell manipulated his equations mathematically, combining and rearranging them, he found that they predicted the existence of self-sustaining waves. An oscillating electric field would generate an oscillating magnetic field, which would in turn generate an oscillating electric field, and so on, leapfrogging through space as a wave. These electromagnetic waves would propagate through empty space, requiring no medium whatsoever. And when Maxwell calculated the speed at which these waves would travel, using only the known electrical and magnetic constants of free space, a quantity called the permittivity of free space, and another called the permeability of free space, he got a number. That number was approximately 310,000 kilometers per second. Maxwell stared at that number. It was too close to the known speed of light to be a coincidence. His conclusion was immediate and breathtaking. Light itself must be an electromagnetic wave, the thing that illuminates our world, the thing that lets us see, the thing that streams from stars across the vast emptiness of space, is nothing more and nothing less than oscillating electric and magnetic fields racing through the vacuum at a speed determined by the fundamental electromagnetic properties of space itself. This was a staggering unification, Light was not some mysterious separate phenomenon. It was electromagnetism. It was the same physics as radio waves, as infrared radiation, as ultraviolet light, as X-rays, as gamma rays. All of these are electromagnetic waves, differing only in their frequency and wavelength, all traveling at exactly the same speed, c, through the vacuum of space. And that speed was not arbitrary. It emerged naturally from the basic constants that describe how space responds to electric and magnetic fields. The speed of light was built into the very fabric of reality. But this magnificent discovery created a puzzle. If light is a wave, what is it waving in? After all, every wave that scientists knew about at the time required a medium. Sound waves need air or some other material. Water waves need water. Waves on a string need a string. What did electromagnetic waves need? The answer that 19th century physicists proposed was the luminiferous ether, a hypothetical invisible substance that permeated all of space. Light waves, they believed, were vibrations of this ether. The ether was everywhere, filling the vacuum of space, and light traveled through it, like sound travels through air. This seemed perfectly reasonable. Every other wave needed a medium, so why not light? But the ether hypothesis made a very specific, very testable prediction. If the ether existed as a fixed background filling space, and Earth was moving through it as it orbited the Sun, then the speed of light should be different in different directions. Light traveling in the same direction as Earth's motion through the ether should appear slightly slower, like swimming with the current versus against it. Light traveling perpendicular to Earth's motion should have an intermediate speed. The differences would be tiny, because Earth's orbital velocity, about 30 kilometers per second, is only about 1/10,000th of the speed of light. But they should be measurable with a sufficiently sensitive instrument, and in 1887, 2 American scientists set out to measure exactly this. Albert Michelson, the same physicist who dedicated his career to measuring the speed of light, joined forces with chemist Edward Morley at Case Western Reserve University in Cleveland, Ohio. Together they constructed the most sensitive optical instrument the world had ever seen, the Michelson interferometer. The device worked by splitting a beam of light into 2 perpendicular beams, sending them along paths of equal length in different directions, bouncing them off mirrors, and recombining them. If the 2 beams travelled at even slightly different speeds, because one was going with the ether flow and the other across it, they would arrive back at the recombination point slightly out of sync, and this would produce a detectable shift in the interference pattern where the beams overlapped. The apparatus was extraordinarily sensitive. It could detect speed differences as small as a few kilometers per second, more than enough to detect the expected ether effect. They floated the entire instrument on a pool of liquid mercury to eliminate vibrations from the building and the ground. They could rotate the apparatus smoothly to test different orientations relative to Earth's motion. They took measurements at different times of day and at different times of year, when Earth's velocity through the hypothetical ether should point in different directions. The result was one of the most famous and consequential null results in the history of science. They found nothing, no difference, no shift, 0. The speed of light was identical in every direction to within the extraordinary precision of their instrument. It did not matter whether they measured along the direction of Earth's orbital motion, perpendicular to it, or at any other angle. The speed of light was the same. They repeated the experiment multiple times. They checked for errors. They improved their apparatus. The result was always the same. Nothing. The speed of light was stubbornly, maddeningly, perfectly constant in every direction. This result was devastating to the ether hypothesis. If light traveled through a fixed medium, and Earth moved through that medium, the speed of light absolutely should have been different in different directions. The fact that it was not meant one of 2 things. Either the ether did not exist, or something very strange was happening to physical objects as they moved through it. The physics community was thrown into crisis. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently proposed a radical idea. Perhaps physical objects actually contract, become physically shorter in the direction of their motion through the ether. If this contraction occurred by exactly the right amount, it would precisely cancel out the expected speed difference, making the Michelson-Morley result come out as null, even though the ether existed. The mathematics worked beautifully, but the idea was deeply unsatisfying. Why would matter contract just because it was moving? There was no physical mechanism It seemed like a desperate patch, a mathematical trick designed to save a dying theory. The scientific community was stuck. Maxwell's equations said light had a specific speed that depended only on fundamental constants. The Michelson-Morley experiment showed this speed was the same for everyone, regardless of their motion. But Newtonian mechanics, the framework that had governed physics for over 200 years, said that speeds should add and subtract in the normal intuitive way. Something fundamental had to give. The stage was set for a revolution. And that revolution came in 1905 from the mind of a 26-year-old patent clerk working in Bern, Switzerland. Albert Einstein, working alone, without access to a university laboratory, without a research group, without even a faculty position, published a paper in June 1905 titled On the Electrodynamics of Moving Bodies. This paper introduced the special theory of relativity, and it would fundamentally transform humanity's understanding of space, time, and the nature of reality itself. What made Einstein's approach so revolutionary was its simplicity and boldness. He did not try to explain why the Michelson-Morley experiment gave a null result. He did not propose new mechanisms or hidden effects. Instead, he took the experimental result at face value and asked a different question. What if the speed of light being the same for all observers is not a problem to be solved, but a fundamental principle of nature to be accepted? What would the universe have to be like for this to be true? Einstein built his theory on just two postulates, two assumptions that he took as foundational. The first postulate was the principle of relativity. The laws of physics are the same in all inertial reference frames. An inertial frame is one that is not accelerating, one that is moving at constant velocity or sitting still. This postulate means that no experiment performed inside a sealed, smoothly moving laboratory can tell you whether you are truly at rest or moving at constant velocity. There is no absolute rest. Only relative motion matters. This idea was not new, it goes back to Galileo, but Einstein applied it with absolute rigor. The second postulate was the revolutionary one. The speed of light in vacuum is the same for all observers, regardless of the motion of the light source or the observer. This is the one that defies every intuition you have developed from living in a world of relatively slow-moving objects. Think about what this means. In everyday life, if you are riding in a car traveling at 60 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the sidewalk sees the ball moving at 80 kilometers per hour. You add the velocities, it is simple, intuitive, and it works perfectly for baseballs and cars and airplanes and everything else you encounter in daily life. But Einstein said light does not work this way. If you are riding in a spaceship traveling at 200,000 kilometers per second, an enormous velocity equal to about 2/3 the speed of light, and you turn on a flashlight pointing forward, you will measure the light leaving the flashlight at exactly 299,792 kilometers per second, and someone standing still, watching you fly past, will also measure the same light moving at exactly 299,792 kilometers per second. Not at 499,000, not at some combined velocity, exactly c. The same for both of you. This seems impossible. It seems like it violates basic arithmetic. If you are moving at 200,000 and the light is moving at 300,000 relative to you, how can a stationary observer also see the light at 300,000 and not 500,000? Something does not add up. And Einstein realized that what does not add up is our everyday assumptions about space and time. For the speed of light to be the same for all observers, the way we measure space and the way we measure time must themselves change depending on how fast we are moving relative to each other. Time itself and space itself are not the fixed, absolute, universal things we always assume they were. They are flexible. They are relative. They adjust to keep the speed of light constant. Let me show you exactly how this works, using one of the most beautiful thought experiments in all of physics, the light clock. Imagine you build a clock that works by bouncing a single photon of light straight up from a mirror on the floor to a mirror on the ceiling, and back down again, over and over. Each round trip is one tick of the clock. The distance between the mirrors is fixed, the speed of light is fixed, and so the ticking rate is perfectly regular. Now, imagine you put this light clock on a spaceship, and the spaceship starts moving at high speed, let us say half the speed of light, from left to right. You are riding on the spaceship, sitting right next to the clock. From your perspective, everything is perfectly normal. The photon goes straight up, bounces off the ceiling mirror, comes straight back down. Tick, tick, tick. Normal time. But now, consider what someone standing still outside the spaceship sees. From their perspective, the spaceship is moving to the right, at half the speed of light. The floor mirror sends the photon upward, but by the time the photon reaches the ceiling mirror has moved to the right. The photon does not travel straight up in the outside observer's view. It travels along a diagonal path, up and to the right. Then it bounces back down, but again the floor mirror has moved further to the right, so the return path is also diagonal. Down and to the right. The path the photon takes, as seen by the outside observer, is a zigzag, and each leg of the zigzag is longer than the simple straight up and down path that you see from inside the spaceship. Now, here is the critical point. The speed of light is the same for both observers. That is Einstein's second postulate. The outside observer sees the photon traveling a longer diagonal path at the same speed c. If the path is longer, but the speed is the same, the time for each tick must be longer. The clock ticks slower, as seen by the outside observer. This is not an illusion. This is not a trick of perception. The clock genuinely ticks slower. And because there is nothing special about a light clock, because any physical process can be used as a clock, this means that all processes on the moving spaceship run slower. Biological aging runs slower. Chemical reactions run slower. The beating of your heart runs slower. Time itself, in every meaningful sense, passes more slowly on the moving spaceship, as observed by the stationary person. This effect is called time dilation, and it is described by a mathematical formula known as the Lorentz factor, represented by the Greek letter gamma. Gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v is the velocity of the moving object and c is the speed of light. At low speeds, the kind we experience in everyday life, gamma is so close to 1 that time dilation is completely undetectable. Even at 1% of the speed of light, about 3,000 kilometers per second, time slows by only about 1/200th of 1%. You would never notice. But as you approach the speed of light, gamma grows dramatically. At 10% of c, time slows by about 0.5%. At 50% of c, time passes at about 86% of the normal rate. At 87% of c, time passes at exactly half its normal rate. At 99% of c, time passes at about 1/7 the normal rate. At 99.99% of c, time crawls at roughly 1/70th the normal rate. And at exactly c, the formula gives a result of infinity. Time would stop completely. But it is not just time that changes, space changes too. If you are on that spaceship moving at high speed, and I am watching from outside, I will measure your spaceship as being physically shorter in the direction of motion. This is called length contraction, and it is described by the same Lorentz factor. A spaceship that is 100 meters long when at rest would appear to be only 50 meters long when traveling at 87% of c, as measured by a stationary observer. At 99.99% of c, it would appear just over 1 meter long. And at exactly c, its length in the direction of motion would shrink to 0. A physical object with 0 length is meaningless, which is another way of saying that a massive object cannot reach the speed of light. And there is a third effect, perhaps the most practically important of all. As an object with mass accelerates to higher and higher speeds, its resistance to further acceleration increases. It becomes harder and harder to push it faster. This is sometimes described as relativistic mass increase, though modern physicists prefer to frame it as an increase in relativistic momentum and kinetic energy. The practical consequence is the same. At low speeds, a given force produces a predictable acceleration. But as you approach the speed of light, the same force produces less and less acceleration. The closer you get to c, the more energy you need to gain each additional meter per second of speed. And to reach exactly c, you would need an infinite amount of energy. Let me put numbers on this to show just how extreme it gets. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, accelerates protons to 99.999% of the speed of light. At this speed, each proton has approximately 7,500 times the energy it would have at rest. 7,500 times. That enormous energy is required just to push the proton from 99.9999 percent of c to 99.999999%. Not even a full percentage point of additional speed. Going from 0 to 99% of c takes a lot of energy. Going from 99% to 99.999% takes even more, and each additional 9 requires exponentially more energy. You could harness every joule of energy in the entire observable universe, and you still could not push a single electron to exactly the speed of light. The barrier is not technological, it is fundamental. It is woven into the mathematics of the universe. This is where Einstein's most famous equation enters the picture. E equals mc squared. Energy equals mass times the speed of light squared. This equation, derived directly from the principles of special relativity, tells us something almost incomprehensibly profound. Mass and energy are the same thing. They are two different forms of the same fundamental quantity, interconvertible through the exchange rate of c squared. And c2 is a colossally large number. The speed of light is about 3 times 10 to the 8th meters per second squared. That is 9 times 10 to the 16th meters squared per second squared. This means that even a tiny amount of mass contains an almost unimaginable amount of energy. 1 kilogram of matter, any matter, if completely converted to energy, would release approximately 90 quadrillion joules. That is equivalent to about 21 megatons of TNT, roughly 1,500 times the energy of the atomic bomb dropped on Hiroshima. From 1 kilogram, the speed of light appears in this equation not as a speed, but as a conversion factor. It is the ratio that connects the world of mass to the world of energy. It appears in equations linking space to time, matter to radiation, gravity to geometry. It is not merely the speed at which light happens to travel, it is a fundamental constant that structures the very architecture of the universe. And the reason nothing can travel faster than it is not because there is some cosmic speed trap enforcing a limit. It is because the geometry of space-time itself is built in such a way that exceeding this speed is not just difficult, it is logically and physically meaningless for any object that carries mass or transmits information. Here is a way to think about this that may help it sink in at a deep level. We do not just live in 3-dimensional space, we live in 4-dimensional space-time, 3 dimensions of space and 1 dimension of time. And everything in the universe, every particle, every object, every person, moves through this 4-dimensional space-time at exactly the same total rate, the speed of light, always, without exception. When you are sitting perfectly still in space, not moving at all of your motion is directed through time. You are moving through time at the maximum possible rate. When you start moving through space, some of your motion through time gets redirected into motion through space. Your speed through space-time does not change. It is always c, but the allocation between space and time shifts. The faster you move through space, the slower you move through time. And if you could somehow reach the speed of light through space, all of your motion would be through space and none would be through time. Time would stop for you completely. This is what happens to photons. Photons have no mass, so they travel at the speed of light through space. From a photon's own perspective, if such a thing could be defined, no time passes at all. A photon emitted from a star 1 billion light years away arrives at your eye from the photon's frame, instantaneously. The entire journey, which takes 1 billion years from our perspective, takes 0 time from the photon's perspective. Photons exist in an eternal now. Now, if all of this sounds like beautiful but abstract theory, let me reassure you, this is among the most thoroughly tested and confirmed physics in existence. Time dilation is not a philosophical concept, it is an engineering requirement. It is built into the technology in your pocket right now. The Global Positioning System, GPS, relies on a constellation of about 31 satellites orbiting Earth at an altitude of roughly 20,200 kilometers. Each satellite carries extremely precise atomic clocks and broadcasts timing signals. Your GPS receiver picks up signals from multiple satellites, compares the arrival times, and triangulates your position. For this to work, the clocks on the satellites and the clocks on the ground must be synchronized to within about 20 to 30 nanoseconds. If they drift further than that, the position calculations become inaccurate. But here is the thing. The satellite clocks drift, They drift because of two relativistic effects working in opposite directions. First, special relativity. The satellites are moving at about 14,000 kilometers per hour relative to Earth's surface. Because of time dilation, their clocks tick slightly slower than ground-based clocks, by about 7 microseconds per day. Second, general relativity, Einstein's theory of gravity. The satellites are higher up in Earth's gravitational field, where gravity is weaker. According to general relativity, clocks in weaker gravitational fields tick faster. This effect makes the satellite clocks tick about 45 microseconds per day faster than ground clocks. The net result of these two opposing effects is that satellite clocks gain about 38 microseconds per day relative to ground clocks. 38 microseconds might sound tiny, but at the speed of light, 38 microseconds corresponds to about 11 kilometers of distance. Without relativistic corrections, GPS would accumulate approximately 10 kilometers of positioning error every single day. Within a week, it would be off by over 70 kilometers. It would be utterly useless. Every time you use GPS to navigate, every time your phone shows your location on a map, relativity is being used. It is being calculated. It is being corrected for. If Einstein had been wrong, GPS would not work. But GPS works beautifully, to within a few meters of accuracy, precisely because Einstein was right. Particle accelerators provide even more direct confirmation. At the Large Hadron Collider, when protons collide at 99.999999% of C, the resulting debris includes unstable particles that decay radioactively. The decay rates of these particles, as measured in the lab, are dramatically slower than the decay rates of the same particles at rest. A particle that should decay in 1 microsecond instead lasts for thousands of microseconds because its internal clock is running thousands of times slower due to time dilation. The measurements match the predictions of special relativity to extraordinary precision. And there is one of my favorite examples: muons. Muons are subatomic particles that are produced in great numbers when high-energy cosmic rays from deep space smash into the molecules of Earth's upper atmosphere at an altitude of about 15 kilometers. Muons are unstable. They have a half-life of approximately 2.2 microseconds, meaning that half of any population of muons will decay every 2.2 microseconds. Traveling at close to the speed of light, a muon should cover only about 660 meters before decaying. Most muons produced at 15 kilometers altitude should decay long before reaching the ground. Yet when physicists set up muon detectors at sea level, they find enormous numbers of muons raining down constantly, far more than should be possible if time were absolute. The explanation is time dilation. Muons from cosmic rays travel at approximately 99.95% of the speed of light. At this speed, the Lorentz factor is about 31.6, meaning the muon's internal clock runs about 31 times slower from our perspective. Its effective lifetime extends from 2.2 microseconds to about 70 microseconds. Plenty of time to reach the ground. And from the muon's own perspective, it is length contraction that saves it. The 15-kilometer distance between the upper atmosphere and the ground is contracted to less than 500 meters, a distance the muon can easily traverse in its own 2.2 microsecond lifetime. Both perspectives, time dilation and length contraction, give the same result. The muon reaches the ground. This is not a thought experiment. This is happening right now, above your head, billions of times every second. Relativity is not just a theory. It is the operational reality of the universe. Now we have established on rock-solid experimental ground that the speed of light is the absolute limit for any object carrying mass, energy, or information. The mathematics forbids reaching it. The experiments confirm this. The technology we use daily depends on it. And yet, as I told you at the beginning of this video, there are real observable phenomena where something appears to exceed this limit. So, let us now enter the truly mind-bending territory. Let us examine every single thing that appears to travel faster than light and determine exactly what is going on. The first and simplest example is something you could demonstrate in your own backyard on a clear night. Take a laser pointer and aim it at a distant wall. Now sweep your wrist quickly. The dot of light moves across the wall. The faster you sweep, the faster the dot moves. Now imagine doing this on a cosmic scale. Point your laser at the moon. The moon is about 384,400 kilometers away. If you flick your wrist by just a small angle, the dot on the moon's surface moves thousands of kilometers. A quick flick of just a fraction of a second can move the dot tens or hundreds of thousands of kilometers. If you sweep fast enough, the dot moves across the moon's surface faster than light. This is not hypothetical. This is simple geometry. At a sufficiently large distance, the angular velocity of your wrist translates to a linear velocity of the dot that exceeds c. You can do the same thing with a shadow. Imagine a giant wall placed far out in space, and you pass your hand in front of a powerful light source. Your shadow sweeps across the distant wall. If the wall is far enough away, the shadow moves faster than light. So, have you just violated Einstein? Have you broken the speed limit of the universe with a $3 laser pointer? No. And the reason why is absolutely crucial to understanding what the speed of light limit really means. The dot on the moon's surface is not a physical object. It is not a single thing moving from point A to point B. It is a sequence of events, different photons hitting different spots at different times. When the dot is at one position on the moon, those are photons from your laser that left the laser, traveled to the moon at exactly the speed of light, and hit that spot. When the dot appears to move to a new position, those are completely different photons that left the laser at a slightly different angle, also traveled to the moon at exactly the speed of light, and hit a different spot. No single photon travels faster than light. No matter or energy moves from the first spot to the second spot faster than light. The dot is not a thing. It is a pattern, an illusion of motion created by independent events. It is like a row of light bulbs turning on in rapid sequence. The wave of illumination can sweep along the row at any speed you like. But no physical thing is traveling along the row. Each bulb is independent, turned on by its own separate signal. This distinction between the motion of physical objects and the motion of patterns or geometric points is absolutely fundamental. Einstein's speed limit applies to objects, to energy, to information. It does not apply to patterns, projections, or mathematical abstractions. A shadow, a laser dot, a spotlight sweeping across clouds, these can all move faster than light because they are not things. They are arrangements of things. No information is transmitted faster than light by the dot's motion. If you tried to use the laser dot to send a message from one side of the moon to the other, the message would still be limited by the speed at which you could redirect the laser and the time it takes the new photons to travel from your laser to the moon, all at the speed of light. This same principle explains the scissors paradox, a delightful thought experiment that has confused many people. Imagine a pair of scissors with enormously long blades, light years in length. You slowly close the handles. As the blades come together, the intersection point where the two blades cross moves outward along the length of the blades. The longer the scissors, the faster this intersection point moves. With sufficiently long blades, the intersection point moves faster than light. Has the scissors beat Einstein? No. The intersection point is not a physical object. It is a geometric abstraction, the mathematical point where two lines cross. No matter is transported outward at superluminal speed. No energy flows from the handle to the distant intersection point faster than light. Moreover, real scissors could not even work this way, because when you close the handles, the motion propagates through the material of the blades at the speed of sound in the blade material, not instantaneously. The far end of the blade would not start moving until the signal from your hand closing the handles reached it, and that signal travels through the steel or whatever the blade is made of at a speed vastly slower than light. The idealized scissors with perfectly rigid, instantaneous blades does not exist because perfectly rigid materials do not exist in a relativistic universe. Here is another apparent violation that trips people up. Consider two particles in a particle accelerator, each moving at 90% of the speed of light, but in opposite directions. From the perspective of someone standing in the lab watching both particles, the distance between them closes at 180% of the speed of light, 1.8 c. That is faster than light. Is this a violation? No, it is not, because closing speed is not the velocity of any single object. Neither particle is individually exceeding c. The closing speed is simply the rate at which the gap between them shrinks, calculated by adding their individual speeds from the lab frame. No single object, no single piece of matter, no single bit of information is traveling at 1.8 c. But here is where it gets really interesting. What if one particle could somehow measure the speed of the other particle, the one coming toward it? Would it see the other particle approaching at 1.8 c? No. And this is where Einstein's velocity addition formula comes in. In special relativity, velocities do not add in the simple way we are used to. If one particle is moving to the right at velocity v1, and the other is moving to the left at velocity v2, the relative velocity as seen by one of the particles is not v1 plus v2. It is v1 plus v2, divided by 1 plus v1 times v2 over c squared. For our two particles, each at 90% of c, the relative velocity is 0.9 c plus 0.9 c, divided by 1 plus 0.9 times 0.9, which gives 1.8 c divided by 1.81, which equals approximately 994 c, less than the speed of light. The velocities add in a way that always keeps the result below c, no matter how large the individual speeds are. This is not a mathematical trick. It is how space-time actually works. Now, let us move to something even more fascinating. When astronomers observe certain quasars and active galactic nuclei, objects powered by supermassive black holes billions of light years away, they sometimes see jets of material that appear to be moving across the sky at speeds greater than the speed of light. These are called superluminal jets, and they have been observed in many objects. The quasar 3C 273, one of the brightest and most studied quasars in the sky, has a jet with components that appear to move at about 8 to 10 times the speed of light. These are real observations by real astronomers using real radio telescopes. Is this genuine faster than light motion? No, it is one of the most beautiful optical illusions in all of astronomy, and it was actually predicted before it was ever observed by the British astrophysicist Martin Rees. Here is what is happening. The jet material is moving at a real speed that is very close to, but still less than, the speed of light, and the jet is pointed nearly, but not quite, directly at Earth. Imagine a blob of material in the jet moving toward us at 98% of c, at an angle of just a few degrees from our line of sight. The blob emits light at one point in its journey, and then, sometime later, emits light again from a new position. Because the blob is moving almost directly toward us, it has almost kept pace with the light it emitted from the first position. The light from the second position does not have much farther to travel than the light from the first position, even though a significant amount of time has passed and the blob has moved a great distance. When we receive both signals, they arrive much closer together in time than the actual time interval between them. This compression of apparent time makes it look like the blob crossed a large angular distance in a very short time, implying a speed greater than light. But the blob's actual speed, calculated correctly accounting for the geometry, is less than c. It is a trick of projection, not a violation of physics. Now, let us talk about something that is not an illusion at all: Cherenkov radiation. This is a real physical phenomenon where particles actually travel faster than light. But before you think Einstein has been disproven, pay very close attention to the details, because the details are everything. The speed of light that we have been calling the universal speed limit, c, is specifically the speed of light in a vacuum, in empty space. But light does not always travel through vacuum. When light enters a medium, a material substance like water, glass, or diamond, it slows down. In water, light travels at approximately 225,000 kilometers per second, about 75% of c. In glass, light travels at approximately 200,000 kilometers per second, about 67% of c. In diamond, light is dramatically slowed to approximately 124,000 kilometers per second, only about 41% of c. The reason light slows down in a medium is not that individual photons are going slower. What happens is more subtle and interesting. Photons enter the material and interact with atoms. They are absorbed and re-emitted, absorbed and re-emitted, countless times as they pass through. Each absorption and re-emission takes a tiny amount of time. The net effect is that the wave of electromagnetic disturbance propagates through the material more slowly, even though each individual photon interaction happens at c between atoms. The macroscopic speed of light through the material is reduced. Now, nothing with mass can travel faster than c, the speed of light in vacuum. but a particle with mass can very well travel faster than light in a medium. If a high-energy electron is moving at 260,000 kilometers per second, it is slower than c in vacuum, which is fine. But it is faster than light in water, which is 225,000 kilometers per second. The electron is outrunning the light waves in the water, and when it does, something beautiful happens. The electron produces a shock wave of light, an electromagnetic equivalent of a sonic boom. Just as an airplane traveling faster than the speed of sound produces a cone-shaped shock wave of compressed air, a particle traveling faster than the speed of light in a medium produces a cone-shaped shock wave of electromagnetic radiation. This radiation is called Cherenkov radiation, named after the Soviet physicist Pavel Cherenkov, who discovered it experimentally in 1934 and received the Nobel Prize for it in 1958. Cherenkov radiation produces a distinctive blue glow, and it is hauntingly beautiful. If you have ever seen photographs of a nuclear reactor submerged in a cooling pool of water, you may have noticed an eerie blue glow emanating from the reactor core. That is Cherenkov radiation. High-energy electrons produced by the nuclear reactions in the reactor core shoot out into the surrounding water at speeds faster than light travels in water. As they outpace the light in the medium, they produce that characteristic blue glow. It is real. It is observed routinely, and it is absolutely not a violation of special relativity, because the particles are still traveling slower than c in vacuum. They are only faster than the reduced speed of light in the medium. Einstein's limit is about the vacuum speed of light, and that limit is perfectly intact. Now, let us get into something more subtle and more mind-bending: the phase velocity of a wave. When physicists talk about the speed of a wave, they actually mean several different things. The most commonly discussed are the phase velocity and the group velocity. The phase velocity is the speed at which the individual wave crests. The peaks of the oscillation appear to move. The group velocity is the speed at which the overall envelope of a wave packet, the lump of wave energy, moves. For light traveling through vacuum, these are the same. Both equal c. But in certain materials they can differ, and the phase velocity can exceed c. For example, when X-rays travel through glass, the refractive index is actually slightly less than 1, which means the phase velocity is slightly greater than c. The wave crests move faster than the speed of light. Does this violate relativity? No, and the reason is both elegant and important. A pure monochromatic wave, a perfect sine wave of a single frequency, is infinite in extent. It stretches from negative infinity to positive infinity. It carries no information because information requires a change, a beginning, an end, a modulation. A wave that is the same everywhere forever says nothing. The information in a light signal is carried by changes in the signal, by the leading edge, by the modulations, by the places where the signal starts and stops. And that informational content, the signal, travels at a speed that never exceeds c, even when the phase velocity does. Think of it this way. Imagine watching waves in the ocean as they hit a long beach at a slight angle. Each wave crest arrives at one end of the beach first, and then sweeps along the beach toward the other end. The point where the wave crest meets the shore, the line of white foam races along the beach. If the waves are coming in at a very shallow angle, this line of foam can move along the beach much faster than the waves themselves are moving through the water. If you could make the angle shallow enough, the line of foam could theoretically move along the beach faster than light. But no water is actually moving along the beach at that speed. The wave is coming in from the ocean. Each point on the beach gets its wave from the ocean, not from the neighboring point on the beach. The motion along the beach is an apparent effect, not a physical transport. Even group velocity can exceed c in certain exotic circumstances. In 2000, a research team at Princeton, led by Lijun Wang, passed a light pulse through a specially prepared chamber of cesium gas and measured the pulse apparently emerging from the other side before it should have. Based on the speed of light, the group velocity appeared to be about 310 times the speed of light. This result made headlines, but the researchers themselves were careful to explain what was really happening. The medium was reshaping the pulse. The leading edge of the pulse, which contained the same frequency components as the rest of the pulse, was being amplified while the trailing edge was being suppressed. The effect was like a person in a line stepping forward, while the people behind stepped back. making it look like the whole group jumped ahead. But the earliest information carrying part of the pulse, the signal front, still travelled at sea. No information was transmitted faster than light. No causality was violated. And then there is a result from 2024 that generated enormous public fascination. Scientists experimentally confirmed something that had been theoretically predicted since the 1990s, that dark points within structured light waves, regions of zero intensity, can move faster than the light wave itself. In these experiments, researchers carefully structured a light beam so that it contained specific dark spots, essentially holes in the light. As the beam propagated, these dark spots moved across the beam's cross-section at speeds exceeding c. The paper was published and widely covered in media with headlines like, "Darkness travels faster than light." It sounds extraordinary, and it is a genuinely interesting result. But it does not violate Einstein's speed limit for the same fundamental reason as the laser dot and the shadow. A dark point is not a physical object. It is an absence of light at a particular location. It carries no energy, because energy is absent there. It carries no information, because you cannot encode a message in the trajectory of a dark spot without first creating the structured light beam that produces it, and the information about how the beam is structured propagates at c. The dark spot is a pattern, a geometric feature of the light field, not a thing. It is like saying the center of a whirlpool can move faster than the water in the whirlpool. The center is a mathematical point, defined by the arrangement of the water, not a physical object being transported. Now, this is a good moment to pause and reflect on something deeply interesting about what we have discovered so far. All of these apparent faster-than-light phenomena, shadows, laser dots, closing speeds, superluminal jets, phase velocities, group velocities in anomalous dispersion, darkness, they share a common thread. They all involve the motion of patterns, not the motion of things. They all fail to carry energy or information faster than c, and this tells us something important about what the speed of light limit really is. It is not a speed limit on everything. It is a speed limit on the transfer of causation, on the propagation of influence, on the transmission of information and energy from one place to another. Patterns can do whatever they want. Mathematical points can zoom across the cosmos at any speed, but nothing that can cause an effect, nothing that can carry a message, nothing that can push or pull, or change or influence anything else, can exceed c. With that principle firmly in mind, let us now enter the strange and wonderful world of quantum mechanics, where the apparent challenges to the speed of light become much more subtle and much more interesting. Quantum entanglement is probably the most famous example of something in quantum mechanics that seems to violate the speed of light. Einstein himself was so disturbed by it that he called it spookhafte Fernwirkung, spooky action at a distance, and he believed it proved that quantum mechanics was incomplete. Here is what entanglement involves, carefully explained. When certain physical interactions occur, they can produce pairs of particles whose quantum properties are linked in a very specific way. For example, if a certain process produces two photons, the laws of conservation may require that if one photon has a vertical polarization, the other must have a horizontal polarization. Before measurement, according to quantum mechanics, neither photon has a definite polarization. Each exists in a superposition of both states simultaneously. They are not secretly vertical or horizontal, and we just do not know which. They genuinely do not have a definite polarization until one is measured. But the moment you measure one and find it to be vertical, you instantly know the other is horizontal, no matter how far apart they are. If you send one photon to a lab in New York and the other to a lab in Tokyo, and you measure the New York photon and find it vertical, you know with certainty, at that exact moment, that the Tokyo photon is horizontal. The determination appears to happen instantaneously across the entire distance. This was demonstrated experimentally by the French physicist Alain Aspect in groundbreaking experiments in 1981 and 1982. Aspect's experiments confirmed that entangled particles exhibit correlations that cannot be explained by any local hidden variable theory, meaning the particles did not have predetermined states that were simply revealed by measurement. The properties genuinely came into being at the moment of measurement, and the correlation between distant particles was instantaneous. In 1997, the Swiss physicist Nicolas Gayssen demonstrated entanglement correlations between particles separated by more than 10 kilometers. And in 2008, Gissin's group showed that if there was some hypothetical signal traveling between entangled particles to coordinate their behavior, that signal would have to travel at a minimum of 10,000 times the speed of light. So entanglement clearly involves some kind of instantaneous connection across space. Does this violate the speed of light? No, and here is why. Although the correlations are instantaneous, they cannot be used to send information. This is proven mathematically by a result called the no communication theorem. When you measure the New York photon, you get a random result, vertical or horizontal, with 50-50 probability. You have no way to choose which result you get. You cannot force the photon to be vertical or horizontal, so you cannot encode a message by choosing what result to produce. And the person in Tokyo, measuring their photon, also gets a random result. They have no way of knowing whether you have already measured your photon or not. The randomness of their result is indistinguishable from what they would get if the particles were not entangled at all. The correlations between the measurements are only visible when you bring the two sets of results together and compare them. And that comparison requires classical communication, which is limited to the speed of light. Think of a simplified analogy. Imagine someone puts one red ball and one blue ball in two boxes and ships one box to New York and the other to Tokyo. When you open your box in New York and see the red ball, you instantly know Tokyo has the blue ball. Information did not travel from New York to Tokyo. The correlation was established at the source when the balls were placed in the boxes. Now, quantum entanglement is actually much stranger than this analogy, because Bell's theorem proves that the particles do not have predetermined states like the balls do. The states are genuinely undetermined until measurement. This is deeply weird and philosophically fascinating, but the practical consequence for faster-than-light communication is the same. You cannot use it to send a message. The no communication theorem holds. Einstein's speed limit survives. Quantum tunneling is another phenomenon that seems to challenge the speed of light, and the discussion around it is genuinely nuanced and fascinating. In quantum mechanics, a particle facing an energy barrier that it does not have enough energy to climb classically can sometimes appear on the other side of the barrier, as if it tunneled through it. This is not science fiction. It happens routinely in nature. Tunneling is essential to nuclear fusion in the Sun. It is the basis for tunnel diodes and scanning tunneling microscopes. It is a well-established, experimentally verified phenomenon. The question that has puzzled and fascinated physicists for decades is, how long does tunneling take? In 1962, Thomas Hartmann discovered something strange in the mathematics of tunneling. He found that the time it takes for a particle to tunnel through a barrier does not increase with the thickness of the barrier beyond a certain point. For thick enough barriers, the tunneling time appears to be essentially constant, regardless of how thick the barrier gets. This is called the Hartmann effect, and its implication is startling. If the barrier is thick enough, dividing its thickness by the tunneling time gives a velocity that exceeds c. The particle appears to have traveled through the barrier faster than light. Experiments have explored this. In 1993, Raymond Chiao and colleagues at Berkeley sent photons through a barrier, a special type of mirror that photons could tunnel through with low probability, and measured the arrival time of the tunneled photons compared to photons that traveled the same distance through air. The tunneled photons appeared to arrive slightly earlier, with the implied velocity through the barrier being about 1.7 times c. In 2019, a team led by Ephraim Steinberg at the University of Toronto performed a sophisticated experiment measuring how long rubidium atoms spend inside a potential barrier during tunneling. Their technique used a quantum clock based on the atom's internal spin to track the time spent within the barrier. The results suggested that tunneling happens astonishingly quickly, consistent with effectively instantaneous traversal of the barrier. So does tunneling break the speed of light? The answer, according to the majority of physicists who have analyzed this carefully, is no, and the reasons are subtle. First, what crosses the barrier is not a particle in the classical sense, shooting from one side to the other. Tunneling is a quantum process involving the spreading and evolution of a probability wave. The wave function of the particle extends through the barrier and has a non-zero probability of being found on the other side. This is not the same as a baseball flying through a wall. Second, the information carrying capacity of tunneling is limited. The signal front, the very first detectable indication that something is arriving, travels at c, not faster. What arrives early in the tunneling experiments is the reshaped peak of a probability distribution, not the earliest possible signal. Third, attempting to use tunneling to send a message faster than light runs into the same fundamental barriers as every other apparent FTL phenomenon. The randomness and probabilistic nature of quantum mechanics prevent you from reliably encoding and transmitting information through the tunnel faster than a light signal could carry it through open space. That said, this is an area of active research, and not all physicists agree on every detail of the interpretation. The question of how to properly define tunneling time remains one of the most interesting open questions in quantum physics. But what is clear, and what every careful experiment confirms, is that tunneling does not enable faster-than-light communication or information transfer. The speed of light limit holds. Virtual particles are another quantum mechanical concept that sometimes gets invoked in discussions about faster-than-light phenomena. So, let me explain what these are and why they do not break the speed limit. In quantum field theory, the mathematical framework that describes the behavior of subatomic particles and forces, interactions between particles are described using Feynman diagrams. These diagrams show particles exchanging other particles to create forces. For example, the electromagnetic force between two electrons is described as the exchange of virtual photons. The strong nuclear force between quarks involves virtual gluons. Gravity involves, theoretically, virtual gravitons. The word virtual is key. Virtual particles are not real particles traveling from point A to point B. They are mathematical objects that appear in the intermediate steps of calculations. In these calculations, virtual particles can have properties that real particles cannot, including, in some formal sense, speeds greater than c, but this does not represent anything physically traveling faster than light. Virtual particles are not directly observable. You cannot detect a virtual photon in flight between two electrons. What you can detect are the real particles and the real forces, and those always respect the speed of light. Virtual particles are the mathematical machinery of quantum field theory, not physical travelers exceeding the cosmic speed limit. The delayed choice quantum eraser experiment is another quantum phenomenon that seems to flirt with faster-than-light influence, and even backwards-in-time causation. This experiment is a variation of the famous double-slit experiment, in which a photon passes through two slits and creates an interference pattern on a screen. But when you try to determine which slit the photon went through, the interference pattern disappears. In the delayed choice quantum eraser version, pairs of entangled photons are created. One photon, the signal photon, goes to a screen. The other photon, the idler, goes to a separate detector where a choice is made, either to measure which slit the signal photon went through or to erase that information. The twist is that the idler photon can be measured after the signal photon has already hit the screen, and the choice to erase or not erase the which path information on the idler seems to retroactively determine whether the signal photon displays an interference pattern or not. This sounds like it allows future decisions to influence past events, which would certainly violate causality and imply some kind of faster-than-light or backward-in-time communication. But the careful analysis of the experiment reveals that this is not the case. When you look at the screen where the signal photons land without any reference to the idler measurements, you see no interference pattern. Just a smooth distribution. The interference pattern only emerges when you take the idler measurements and use them to sort the signal photons into groups. Each group, selected based on a particular idler measurement outcome, shows either an interference pattern or no interference pattern. But these subpatterns are invisible without the sorting information from the idler detector. And obtaining that sorting information requires classical communication, which is limited to the speed of light. No information travels backward in time. No signal is transmitted faster than light. The correlations are real, but they are only visible in retrospect, after both measurements have been made and compared. Now let us scale up dramatically. Let us leave the subatomic world and look at the largest scales of the universe, because this is where the most dramatic apparent violation of the speed of light occurs. And unlike the phenomena we have discussed so far, this one involves real, physical distance increasing at a rate that genuinely exceeds the speed of light. I am talking about the expansion of the universe. In 1929, the American astronomer Edwin Hubble made one of the most important discoveries in the history of astronomy. By measuring the distances to other galaxies and comparing them with the redshift of their light, Hubble found that galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This relationship is now called Hubble's law, and it is described by a simple formula. The recession velocity equals the Hubble constant times the distance. The Hubble constant is currently measured to be approximately 67 to 73 kilometers per second per megaparsec, where a megaparsec is about 3.26 million light-years. This means that for every additional megaparsec of distance, a galaxy appears to recede an additional 67 to 73 kilometers per second faster. At a certain distance, the recession velocity exceeds the speed of light. Working with a Hubble constant of about 70 kilometers per second per megaparsec, this happens at a distance of about 14.4 billion light-years. This distance is called the Hubble radius. Beyond the Hubble radius, galaxies are receding from us faster than light. The observable universe has a radius of about 46.5 billion light-years. Galaxies at the edge of the observable universe are receding from us at roughly 3.3 times the speed of light. Galaxy GN Z11, one of the most distant galaxies ever observed, discovered in 2016 with a redshift of approximately 10.6, is currently about 32 billion light-years away and receding faster than C. So there are real galaxies right now moving away from us faster than the speed of light. And these are not abstract mathematical patterns or geometric tricks. These are real galaxies with real stars and real mass. How is this possible if nothing can exceed the speed of light? The answer lies in a critical distinction. These galaxies are not moving through space faster than light. Space itself is expanding, and the galaxies are carried along with it. This is fundamentally different from what Einstein's special relativity prohibits. Special relativity says that no object can move through local space-time faster than c. But the expansion of space is not motion through space. It is the growth of space itself. Imagine drawing two dots on a balloon and then inflating the balloon. The dots move apart, not because either dot is moving across the surface of the balloon, but because the balloon itself is getting bigger. The further apart the dots are, the more rubber there is between them, and the more rubber is expanding, so the faster they separate. Neither dot is moving in any local sense. The rubber under each dot is stationary relative to the dot, but the total effect of all that expanding rubber adds up, and at sufficient distances, the separation rate exceeds any speed you like. The physicist Sean Carroll put it perfectly when he said that comparing the expansion rate of the universe to the speed of light is like comparing the height of a building to your weight. They are different types of quantities that do not directly compete with each other. The expansion of the universe is described by general relativity, Einstein's theory of gravity, not by special relativity. General relativity allows space itself to stretch, compress, warp, and curve. Objects within a small local patch of space are still limited to subluminal speeds, but the large-scale behavior of space itself is under no such constraint. This leads to some truly staggering consequences, because the universe is expanding and the expansion is accelerating, driven by the mysterious dark energy that makes up about 68% of the universe's total energy content. There is a cosmological event horizon. This is the distance beyond which light emitted today will never reach us, no matter how long we wait. The cosmological event horizon is currently about 16 billion light-years away. Any event happening now at a distance closer than 16 billion light-years will eventually send light that reaches us. But any event beyond that distance is forever causally disconnected from us. The light simply cannot outrun the expansion. And because the expansion is accelerating, this event horizon is getting closer. More and more of the universe is falling beyond our ability to ever observe or interact with. In the far distant future, hundreds of billions of years from now, our local group of galaxies will be the only thing visible. Every other galaxy will have been carried beyond the horizon by the relentless expansion of space. The universe we can see will shrink even as the universe itself grows without limit. Now, let us consider the most extreme version of faster-than-light expansion in the history of the universe. In the first tiny fraction of a second after the Big Bang, during a period known as cosmic inflation, the universe underwent an incredibly rapid exponential expansion. Inflation is believed to have occurred between approximately 10 to the minus 36 seconds and 10 to the minus 32 seconds after the Big Bang. During this almost incomprehensibly brief period, the universe expanded by a factor of at least 10 to the 26th, and possibly much more. Regions of space that were initially close enough to exchange light signals, close enough to be in causal contact, were flung apart so rapidly that by the end of inflation, they were separated by distances far greater than light could have traversed in the time since the Big Bang. This is why the cosmic microwave background radiation, the afterglow of the Big Bang that fills the entire sky, looks so remarkably uniform in every direction. In every direction you look, the temperature of this ancient radiation is the same to within 1 part in 100,000. But the regions on opposite sides of the sky are now separated by 93 billion light-years, far too far apart for them to have ever communicated with each other at the speed of light in the age of the universe. How can they be at exactly the same temperature if they never exchanged any signal? The answer is inflation. Before inflation, these regions were close together in causal contact and had reached the same temperature. Then inflation blew them apart to enormous distances. No signal needed to travel between them after inflation. The uniformity was established before the exponential expansion separated them. And once again, inflation does not violate Einstein's speed limit. Nothing moved through space faster than light during inflation. Space itself expanded, carrying everything apart. Locally, in any small patch, nothing exceeded c. But the cumulative effect of the expansion over the entire volume of the universe produced effective separation rates far exceeding the speed of light. Now, let me take you to one of the most dramatic episodes in the recent history of physics. A story that captivated the world and showed just how deeply the speed of light limit is embedded in the foundations of modern science. In September 2011, a team of physicists working on the Opera experiment made an announcement that sent shockwaves through the scientific community and ignited a media firestorm. Opera, which stands for Oscillation Project with Emulsion Racking Apparatus, was a neutrino experiment based at the Gran Sasso National Laboratory in Italy, deep inside the Apennine Mountains. The experiment was designed to study a phenomenon called neutrino oscillation, the way neutrinos change between different types, or flavors, as they travel. Neutrinos were produced at CERN in Geneva, Switzerland, and fired through the Earth, traveling 730 kilometers underground to the detectors at Gran Sasso.